Good afternoon, sir.
Good afternoon, Rupinder. Let's wait for some time, then we'll begin.
Sure.
Are you still traveling or
Yes,
you're
sir. I am
home?
still in metro, sir.
Very good, very good. So I was
एक्चुअली
thinking
सर मंडे
like
को क्लासेस 5 बजे तक होती हैं तो लेट हो
right.
जाता
हाँ. मैं यही सोच रहा था कि 5-10 मिनट जो लास्ट क्वेश्चन है वो करने के लिए दे देते हैं. उसके बाद मैं एक्सप्लेन करता कि कैसे डिराइव करना है, क्योंकि उसमें कुछ डेरिवेशन करना पड़ेगा छोटा मोटा.
है। ओके।
हम्म. तो तुम सोच सकते हो, अभी क्वेश्चन शायद तुम्हारे स्क्रीन पे है. अगर
यस सर।
पेन पेपर निकाल सकते
सर
हो तो
एक्चुअली
ट्राई कर
मैंने ये भी
सकते हो.
करा है मतलब, बट वही है, फिर रफ कॉपी कर पे अभी
ठीक है.
मैंने ट्राई तो करा।
गुड. We are waiting for other people to join, and if you can try solving the last question 2.11. I'll give first 5 to 10 minutes for that question. You try it, then I'll show the solution. All right. I think we have given enough time. Now I will solve it. Okay. Mm, okay. So the situation is like this. We have a wing. It's not rectangular, but I'm just drawing it rectangular. Can you hear my voice clearly?
Yes.
All right. So this is fuselage center line. Idea is if there is some side slip beta because of roll.
Sir, are you saying something?
What happened? All right. So the question is, if we want to enforce certain value of CL beta, then what would be the dihedral angle for us? Dihedral angle is this angle.
Hello, sir.
Yeah, I can hear you. What are you trying to say? You have anything to say? All right. So the question is, we have to find out a certain value of CL beta, which is 0.1. How can we ensure this value? So CL is moment coefficient about which axis? If this is x-axis, this is y-axis, and perpendicular to this paper, there is z-axis. So CL coefficient is the moment about which axis? Om? Rena? We can't hear you. All right, I'll try. Just wait for a few moments. Can you hear me now?
Yes, sir, we can hear you.
All right. So the question is, CL is the moment coefficient about which axis, x, y, or z? Rupinder? I think he can't hear us. Om, if you know the answer. Reina, you know the answer. CL is the coefficient of moment about which axis?
Why?
Y-axis. Okay. Om? Rupinder?
Yes, sir.
CL is the coefficient of moment about which axis? X, Y,
Sir,
or Z?
CL,
Yeah.
the coefficient of lift it is, but you are asking about axis.
Yeah. Actually, there are three coefficients: CL, CM, and CN. These are three moment coefficients, no? So CL belongs to which axis? X-axis. CM belongs to Y-axis. CN belongs to Z-axis. So there are three moments that we define: capital L, capital M, capital N. Okay.
And when we define corresponding moments, then moment coefficients, so they are CL, CM, and CN. And you're talking about the lift coefficient, so we are not talking about that lift coefficient right now. Okay, so CL is the moment coefficient about x-axis, which means the aircraft is going to roll about x-axis. So that's why we are saying that we want to provide it the roll stability. If the aircraft rolls for some reason, it should have the ability to restore its what do you call the roll angle. Let's say the roll angle is phi is equal to 0. You're maintaining it, but for some reason it was disturbed from that 0 position, so it went to certain non-zero angle. Phi is equal to, let's say, 3 degrees. Now, if your aircraft has a dihedral of certain magnitude, then the aircraft has a tendency to roll it back to phi is equal to 0. So that tendency we want to establish, and the question is about how much should be this angle. Okay, the dihedral angle. If everyone is aware about the dihedral angle, it is the angle from horizontal, between the wing plane and horizontal. Okay, so that's the idea. If you look at the question again, the question is saying, suppose the wing planform in problem 2.10 is incorporated into a low wing aircraft design. Find the wing dihedral angle necessary to produce a dihedral effect of CL beta. Okay, now this effect is called dihedral because of the existence of angle gamma, this gamma. Okay, there exists a tendency of the aircraft to return back to 0 roll angle. It has a roll stability, in other words. Now, it's at CL beta. So I want to be sure that everybody understand what CL beta means. Om, do you understand what CL beta means? Reena, do you understand what CL beta
Yes,
means?
sir.
What does it mean?
The dihedral effect.
Oh, no. That's okay. It's dihedral effect, but this quantity, I mean, CL is the rolling moment.
Coefficient of lift.
No, it's not coefficient of lift. It's coefficient of moment. I'll define it for everyone's convenience a little later. But for the time being, when we write CL and then we write beta in the subscript, what does that mean? It means we're differentiating CL with respect to beta. That's what I wanted to ask. CL beta means that thing. Yeah. So now the time comes, we define CL first. So why do CL exist? It is because there exists extra lift when the aircraft is rolling. So when the aircraft rolls on one of the wing, one of the wing experiences more lift. For example, if we look from the front, if aircraft is rolling like this, then because of the side slip angle, okay, I have explained it in other video why side slip comes into existence, but right now just follow with me. A velocity component from this side will be approaching the aircraft when aircraft rolls by some angle. Okay, now one component of this v, that is a side velocity, is directly perpendicular to the wing, and this component increases the angle of attack. So there will be an extra lift on this wing, and there will be a reduction of lift on this wing. So what will happen is, if you look at the center point, from the center point there is a lift, so that lift is trying to roll it back towards 0. Okay, that is what is happening here. That is what we call dihedral effect. Because of the dihedral, there exists an increased angle of attack and corresponding lift whenever aircraft rolls. Our question is, enforce this CL beta and compute the value of this angle gamma. So what should be the gamma such that a certain value of CL beta can be enforced? Now, before CL beta can be enforced, we need to understand what CL is. So for that, I will define L, the rolling moment about x-axis. So what will happen is there will come a change in lift on one of the wing, and there will be a reduction of lift on one of the wing. So let's call it delta L, let's call it minus delta L. Guys, I'm receiving a call. I'll just come back in a moment.
Okay, sir.
All right. Sorry for the delay, guys. I had an important call, so I had to take it. So now we continue. The idea is,
Sir, can you show the question again?
yeah, I'll show the question again. You take the screenshot of this question so you can look at it.
Okay, sir.
Yeah.
Got it.
All right. So okay. So when we want to compute the moment about x-axis and the force is acting at a certain distance. Now, can any one of you tell me, only consider one part of the wing? Let's say half wing. Okay. Let's say this the wing on the right, and this is the wing on the left. Now tell me, where will the net force will act for a given geometry? Like your aircraft wing could be like this also, as shown in the question, like this also, right? Could be some sort of delta wing. So half wing will be like a triangle. Okay, it could be any shape, but the question is, at what point the net lift will act, so that we can compute the moment about x-axis. Because by moment I mean force multiplied distance. So the distance is unknown to us. We know the change in force somehow. We'll compute that. We have already discussed in one of the classes, but I'll discuss it again, how much lift is generated when aircraft rolls. But the critical question is, at what distance that change of lift will act. You understood the question, right? Rupinder?
Yes, sir.
Yeah. So I'm expecting that all of you understood the question. Now try to think about it. At what point the change of, or rather say, the entire lift is going to act for a arbitrary shape of the wing. So what is that point?
Sir, the main force acts through the point of CP, which is we assume it is at the aerodynamic center.
Okay.
But the distance, can we say it is at the midpoint between the root and the tip?
Can you say for that for an arbitrary geometry?
No, sir, I can't.
Yeah. For a rectangle, you can say it. You can say that. So your answer was right earlier. It will act on mean aerodynamic center. But the question is, can you find the mean aerodynamic center in any case? Let's say I give you this particular geometry. Can you find out where will the aerodynamic center will exist and where will be the mean aerodynamic code? Let me make it more clearer. So this is one of the wing that you have, wing section. Our question is, at what point from this line, the vertical line, the net force will act? Okay.
We can, sir.
Yeah. Tell me how we'll compute that.
Sir, we need two things. First is the taper ratio. What is the taper ratio of the wing? And
Okay.
second is the sweep angle.
Very good. So let's say I give you a
Sweep
sweep
angle.
angle of, let's say, some gamma. I also give you a root chord and the tip chord and the lambda, which is CT divided by CR.
Yeah,
So this
yes.
is taper ratio, this is gamma. Now tell us what is the answer for mean aerodynamic code and the location of aerodynamic center.
Sir, there are 1 and 2 formulas. I cannot remember them properly,
Okay.
but one of them includes 1 minus or plus lambda square divided by 1 plus lambda square.
Yeah,
Something
right.
like that.
Right. So I just wanted to know that you are aware of such an expression. All right. So there exists an expression by which you can compute where this line will exist. We call this line mean aerodynamic code. Okay. So first thing we have to do is find out the length of mean aerodynamic code C bar. It is usually given as 2/3.
Yes, sir. CR. Oh, yes, sir. This one.
Yeah. In terms of CR, then probably some 1 plus lambda square plus lambda, I believe, divided by some 1 plus lambda. I also don't remember exact expression, but it looks like this. Root code is used and some factor 2/3. Lambda is the taper ratio. So by that, you find out the C bar. C bar is what? This length from here to here. Okay. So what will happen is C bar can only have one place. C bar cannot be here because it's less than C bar, and it cannot be here. So it will be greater than C bar. So C bar has a unique place on the wing, right? Once you find out C bar, the length, it will have a unique place. And on this C bar, when you come C/4 from the leading edge, there exists your what do you call aerodynamic center. Got it? So this is the location where aerodynamic center will exist. But once we localize the C bar, where is this length from here, this distance y, we can compute that moment. All right. So since we have the geometry, all of the required numbers are here, we can compute this location C bar. And corresponding to that C bar, we can find out what is this length y from this vertical line here at the root. Okay. So now I hope it is clear to you that given the geometry of the wing, you can find out a point at which the net lift is acting. All right. So let's call this length some y bar for the time being. Okay. And how much force is acting at that point? Delta L. Okay. Change of the force. So that is delta L. We were about to compute L. So that will be delta L multiplied y bar. Is everybody following the discussion?
Yes, sir.
Yeah, all right. So delta L times y bar. So that would be the moment about x-axis. Okay. Now, how do I compute the change of lift? This was discussed in one of the lectures when the aircraft rolls, how much extra lift is generated. So we ended that lecture with the conclusion that whenever aircraft rolls, because of the side wind, the leading wing, which is into the roll, the leading wing, which is going, let's say if the aircraft is rolling towards right, okay, so the right wing is going down, so the right wing will experience a increased angle of attack by how much magnitude? Can anyone recall? Can you recall how much angle of attack, change in angle of attack is experienced when the aircraft is rolling? It was equal to gamma times beta. Okay, gamma is that dihedral angle and beta is the side slip angle. Okay, side slip angle means you're looking at the aircraft and this is the x-axis of the aircraft, but the relative wind is coming from this direction. So this is angle beta. So delta alpha on the leading wing is this magnitude. So corresponding to this delta alpha, you will have a delta lift that will be CL of the wing multiplied delta alpha, right? CL alpha. What else? What else I have to write to compute the lift? Huh? Sorry? Yeah. It will be CL alpha, not CL. Then there will be Q infinity, the dynamic pressure, and the wing area. Okay. That's how you compute the change in lift. So the idea is, since the lift is being lost here, minus delta L, but the idea is that this lift, this extra delta L change and this delta L change, the moment is in the same direction. Okay, they are producing a moment in the same direction. This minus delta L can be thought of a force acting like this. Okay, now if you imagine you're sitting here, this is generating a counterclockwise moment. So this force is also generating a counterclockwise moment in this plane of the paper that we're looking at. So the total moment will be 2 delta L times y bar. Y bar is the location of the aerodynamic center. And delta L, the change of lift we have already computed here, which is twice of now dynamic pressure at the wing, CL alpha. Delta alpha is already gamma times beta. S is the surface area of the wing. Y bar is the aerodynamic center's location. That will be the moment. Okay. Now, how do we compute CL, the coefficient of moment for this x-axis? Reina, how do you compute CL from L? L is not lift, it's moment. Okay. So before that, let's say L is lift. How do you compute the lift coefficient? What do you do with lift? You're not audible. Ripinda?
Yes, sir.
What do we do to find out CL from the lift?
Sir, you mean its purpose you are asking?
Not purpose. I'm asking how. Like what should be done?
Okay, lift divided by Q infinity
Hmm.
and S.
Yeah. And how about CL from this moment, roll moment?
Divided by maybe by here. Y bar, I guess.
B, wingspan.
Okay, got it.
Okay, so you divide dynamic pressure, surface area of the wing, and wingspan. So this is your CL. What you end up with, Q CL alpha gamma y bar divided by B times beta. So what will be CL beta? Om, what will be CL beta? He's joining again. Reina, what will be CL beta? If you know the expression for CL, this expression. Repinder, what will be CL beta? Can anyone hear me?
Yes, sir.
Yeah. So the question is, what will be CL beta? We have already derived CL. So from CL, how do we get CL beta? Reina, do you know? How do we get it? Okay. So I discussed it a little while ago. So if this is CL and CL beta, it's actually this DCL or D beta. So differentiating CL with respect to beta. So when you differentiate this CL with respect to beta, what do you get? Anyone? We can't hear you. I think your mic is unmuted, but we can't hear you. Okay, it will be C. I don't know what's
B square.
so beta. So this will be the expression CL beta.
Yes.
Now we are asked that this expression should have a value 0.1. So when we were solving this question from the beginning, we knew CL alpha. We decided it based on the wing geometry and the theoretical value of airfoil, this CL alpha. Okay. And gamma is required to be found out. Y bar you can find out from the geometry. B is also from geometry. So you know everything. Only unknown is gamma. You can find out gamma from this expression. Now the question is, how do you find y bar and what is the value of CL alpha? B is pretty simple. So these two values you need to be able to find out. So CL alpha, how would you find out? How will you find out? What you do is you find out the CL alpha for an airfoil, and that is 2 pi theoretical value. So now since you have a wing, you know the aspect ratio of the wing. Okay, so based on that aspect ratio, there exists an expression that can give you CL alpha of a finite wing, and I think it looks like this probably. Pi and aspect ratio. AR is aspect ratio. I hope everybody understand what aspect ratio is. CL alpha is 2 pi, and from here you can find out what?
Right, aspect ratio and value of E.
There is also an E. So we usually assume that E is 1.
So,
Yeah. So I think now only thing is we need y bar. So that also you can do from geometry. I already explained how do you find y bar. So I'll do that again for everyone's clarity. First, you are given wing geometry, so you know the root code, you know the tip code, you know this angle gamma, you know Cp over Cr, which is lambda. Okay, and from there you find out the C bar. Okay, mean aerodynamic code, and that is 1 divided 2 by 3, 1 plus lambda square divided by 1 plus lambda times Cr. So some factor of the root code. Let's say you find that length here. Now you don't know how far that length is from here, so you need to apply some geometry. Okay, you need to apply some geometry, and from there you can find out this y bar. So that's how you proceed. I can also explain this geometry, but let's not discuss it now, because in the last lecture also I discussed a little bit about this kind of geometry. I hope you can solve it using some straight line equations and all. Okay, so we have discussed this entire question. That is good. You have had some experience with this computing and designing vertical stabilizer also. Yeah, that is good. Now we can move to, I think, the assignment questions in the 7th assignment. So this was the first question. I hope you can see the screen. If thrust to weight ratio increases, then the takeoff distance of the aircraft will. Anyone wants to answer, they can answer. So what we are doing here is, this is T by W. We are increasing T by W. And then we are asking what happens to the takeoff distance. Somebody said decreases, right?
Yes.
And what's the logic?
That's thrust to weight ratio increase. It means thrust is increasing. It
Right.
will overcome the weight, I guess.
Very good. I mean, it's pretty intuitive question. Okay, but apart from that, we must understand what actually takeoff distance is.
Yeah, also by formula.
Yeah. Formula is important, but we must understand conceptually what takeoff distance is. Like technically, what is takeoff distance? Let's say you begin the aircraft rolling from here. So it's not rolling, it's ground roll basically. Ground rolling, you start from this point, let's say A. Now you're on the ground on the runway, you're moving. At a certain point, you lift off from the ground. Okay, at a certain point, you lift off from the ground, you start climbing. Now, is it, let's call this point B. Is it takeoff distance?
No.
So which one is the takeoff distance? This
The
one?
point at which the aircraft will clear the minimum screening.
Exactly. So I'm happy that you know the answer. So the thing is, I brought some geometry here. Yeah, it looks like this. So you start the ground roll here. At certain point, you lift off from the ground. Okay, so you call it SG, ground roll. And after that, you have A. You're in air, so it's in some A subscript. So airborne. You're in the air, so this is airborne distance. And you define some number, and when it clears that number, corresponding to that distance, you call the takeoff distance. So your airport should be able to provide this takeoff distance, the clearance of the geometry, clearance of the height. So there should not be a large building in the vicinity of a runway. It should be far away. Aircraft should be able to clear this distance. Okay, yeah, good. I'm happy you know the answer. How about question 2? The load factor of aircraft during the transition phase of takeoff maneuver will be
Greater than 1.
why?
Because sir, we need lift greater than our weight if we want to climb.
Yeah.
So that's
That's right. You need more lift because we're basically going into the air. So lift is greater than the weight. Load factor. And what is load factor's definition?
L by W.
How about 3? The ground roll distance. So now we have the technical term here. The ground roll distance is related to thrust reversal as
1 by thrust reversal.
1 by thrust reversal. Why?
Obviously, the thrust reverse means the brakes are applicable in the distance covered will be less.
Yeah, you're right. Reena, did you understand what he said?
No, sir.
Can you speak again, Om?
As thrust reversal will increase, the opposing force on the aircraft will increase, and thus it will have to cover less distance to stop.
Did you get it now?
Yes, sir.
Yep. So the idea is, let's say this is the runway. Aircraft is coming like that. At some point, that touchdown happens, and then it's moving on the ground. So you are applying some opposing force, and the larger the force, the distance covered will be minimum, right? You can stop it quickly if you have a thrust reversal. So that's the idea. Question 4. What's the answer for question 4? Takeoff distance is related to thrust as
Inversely, first
First option.
yeah, and the logic is similar, I guess, as the previous logic. Like your something is moving on the ground, the large force you have, they will pick up speed quickly, right? So I think I have one photograph which defines how aircraft is picking up velocity. So you're here on the ground at 0 speed, you accelerate until some vstall. What is vstall? I'll ask the definition of all of these numbers so that you understand what happens in the takeoff maneuver. What is vstall first?
minimum velocity required for cruise.
For the aircraft to remain airborne, right? Then what is VMCG? VMCG.
Minimum control speed on ground.
Very good. This minimum ground control speed. And what does that mean actually? What does ground control speed
Pardon,
mean?
sir?
What does ground control speed means?
Sir, it is a speed at which we have a nose wheel to maintain the center line of minimum speed.
Yeah.
After that, it will be difficult.
Yeah, we got your point actually. Your voice is breaking, but I understood what you're
Or
trying
we
to say.
can still become effective after this speed.
Right. So basically, the control surface like radar becomes effective at this speed on the ground. So you can effectively use radar while being on the ground. So that at that speed, you call it MCG, minimum ground control speed. And how about VMCA? Wait. Minimum ground control speed.
Minimum control speed in air for airborne.
Yeah, very good.
The aircraft is
Airborne.
airborne.
So this number is just for reference here because the aircraft is still on the ground, so it doesn't have real value. Okay. So it's just saying that when aircraft accelerates, so it crosses vstall first, then it crosses VMCG, and then it accelerates further. Okay. Then it comes to the VMCA. So the idea is if your aircraft is flying below VMCA, the control surfaces might not be very effective, okay, while flying. So this number is for reference here. And how about this? I don't know if it's VL or V1. Let's call it VL. Okay. So what is VL?
Said to be V1.
Right. Can you explain what does that mean actually?
When the velocity required for the takeoff is achieved.
It's so when you
V1
cross
is
this
the
speed,
decision speed.
what did you say?
V1 is the decision speed.
Decision speed, right? Is V1, huh? So we got it V1. It's the decision speed. Decision of what?
To either take off or abort.
Yeah, to take off or abort. So you do not abort after this. You just take off, and before it you can abort. So this is the decision speed. All right. If you are at it, if engine failure happens, you will still take off. What is VR?
Rotate speed. Rotation speed.
And what happens at this speed?
We give elevator input to so that the aircraft nose just moves up.
Right. And what is VMU?
The whole the undercarriage also lifts up at this speed.
All right. And what is VLO?
Lift off when the aircraft is properly airborne.
So I completely could not understand what VMU is. Can anyone explain?
Sir, it is the speed at which the main landing gear just takes off from the runway. Just and VLO is the velocity at which aircraft maintain its climb angle, attains its climb angle at which it was set.
Okay. Okay. All right. So yeah, we are now at the fifth question. What is as the flap deflected during landing, the ground roll distance will
Decrease.
what is the answer? When flap
Decrease
decrease. Why?
because the flaps increase the lift, but as well as the drag.
Okay.
Drag is what we need to stop the aircraft
Very good.
at ground.
Right. Absolutely. So I think last assignment was rather easy, huh?
Yes.
Yeah. Okay. So this is it for today. I didn't have many more questions. So you guys, if you want, you can leave. I'll put it put this meeting on run because it needs to be 2 hours and I don't have more content for today. So you guys can leave. Okay.
Sir,
Yeah.
sir, before leaving, sir, I wanted you to please show me again how CM naught and CL alpha. CM naught should be positive and CM alpha should be negative
Okay.
mathematically. I mean, I know why that their signs are this, but I don't understand why their signs are like this. So CM naught and CM alpha.
Okay. So this is CM, this is alpha. Usually they say it should be like this. So CM can be written like as a straight line. Now CM alpha is the slope of this line. CM alpha, CM naught is this distance intercept. Question is why this? So let's ask the counter question. Let's pass it through origin. Okay. let's pass it through origin first. And in one case, let's pass it through negative intercept. Okay. Now let's try to see what happens when the aircraft is pitched. So first, let's consider this case 1, 2, and 3. Let's consider the case number 2, which is usually shown. So at what angle of attack aircraft will be pitched? So this is the angle of attack. This is the value of Cm. At what value of the Cm the aircraft will be pitched? By pitching, I mean when it's flying steadily in steady flight, what should be the value of Cm?
It will be positive, sir.
I lost you.
It will be
It should
positive,
be
sir. Positive.
What do you think? What should be Cm when the aircraft is pitched at a certain angle of attack?
It can be both ways. Positive.
Reena, what do you think? When the aircraft is flying steadily, what should be the value of Cm?
Positive.
Positive. Okay. Unfortunately, all of you are wrong. Cm should be 0. If imagine a situation if Cm is non-zero, Cm is either greater than 0 or Cm is less than 0. What is going to happen? The aircraft will experience a pitching moment. So if Cm is greater than 0, it means there is a pitch up moment acting on the aircraft. How do you define moment? Moment
Force
is
into
defined.
distance.
That is okay, but in terms of Cm, you have dynamic pressure, Cm alpha, or other Cm, then C bar, surface area. That's how you
Yes.
define it, right? So when Cm is 0, this number, because you are flying at a certain speed, so you have half rho v square, Q infinity is half rho v square. So you have a certain dynamic pressure, a positive number. C bar is a constant positive number, surface area is a positive number. The only number that is dictating whether the aircraft will pitch up or pitch down is Cm. This is the number which is dictating that. Okay, so let's imagine this is the fuselage reference line and this is the wing, a certain angle of attack you have. Okay, now aircraft is flying like this. If there exists a Cm which is non-zero, so the next moment what will happen is the fuselage will try to go up, let's say, right? Then it will try to go up again, will try to go up again, and it will become vertical. Your aircraft will become vertical if Cm is greater than 0 for a large amount of time. Similarly, if Cm is less than 0, the aircraft will pitch down. So you understand what it means. This M should be 0. That is what we call equilibrium. All summation of all moments should be 0. And when the summation of all moments
What
acting on
happens
the,
if it is greater than 0?
yeah, that is stability, that it should return to 0. So that happens because Cm has a special behavior. Whenever angle of attack changes, this number Cm changes in a certain fashion. That fashion we want to discuss later, but first we want to understand what it means to be pitched. When the aircraft is flying steadily, you usually say lift is equal to weight, thrust is equal to drag, and you forget that total M should also be 0. Total moments. And total moments, I mean L should be 0, M should be 0, N should be 0. But right now, Ripinder asked me the question about M only. So M should be 0. So whenever M is 0, Cm should be 0. Okay. So now let's come back to this graph. Graph number 2. At what location, at what angle of attack Cm is 0? Right? This is the location here. This is 0 Cm. This is non-zero Cm at this angle of attack. So this is the angle of attack, alpha, right? Pitch. So aircraft is being pitched at this angle of attack. Is it clear so far that why should Cm be 0?
Yes, sir. It is clear.
Very good. Now it's clear that CM should be 0. Now it is also clear that when CM is 0, there will be an angle of attack corresponding to that, right? So in this case, angle of attack is greater than 0. In this case, what is the pitching angle of attack? In this case, the third case.
Yes, sir.
Huh?
Zero angle of attack.
Very good. Alpha is 0 for CM being 0. Alpha is positive for CM being 0. How about this?
Which one, sir?
Angle of attack is negative for CM being 0, right? It's 0 here.
Yes,
Angle of
sir.
attack.
Sir,
Ah,
sir, I got a point, sir. CM naught is the movement coefficient when angle of attack is at zero lift angle of attack. So at zero lift angle of attack, which is mostly negative for positively cambered aerofoil. So that means if the aircraft is flying at a negative angle of attack, the movement created will help the air wing to rotate in the positive nose up direction. So the aircraft will pitch up and stabilize it again.
I find your explanation slightly complicated. Okay, you are absolutely right in what you are saying, but I still want to make it simpler for you. Just look at this graph. Okay.
Yes, sir. Yes, sir. Same here, sir. But I also didn't get my explanation corrected for the CM alpha term, like why it should be negative. Yes, sir.
So
You
that,
please continue, sir.
yeah. So first I just want to repeat whatever he said, maybe in simpler language. So he said, let's say you are flying at this. CM is 0 because you are in equilibrium. So CM has to be 0. Angle of attack is greater than 0. You need greater than 0 angle of attack for CL to be something like CL alpha graph is like this. So if angle of attack is positive, then CL will have a certain significant value. You want CL to be large, slightly larger. Okay, you don't want to be very small. So that for that reason, alpha should be positive. That you can pitch the aircraft at a positive angle of attack. Okay. Now, what happens if let's say for some reason alpha increase? Now you have a negative pitching moment. So what will happen? Angle of attack will be decreased from this point. So when it decreases, let's say it goes here. Now what happens is you are at a positive CM. Whenever positive CM happens, alpha will be increased. So it will increase. So it's acting like a spring. Okay. So it is the equilibrium point. You go this way, you come back. You go this way, you come back. So it is the equilibrium point. So the aircraft remains at this equilibrium location. Okay. Now just change it. Change the slope slightly like that. And it's the CM, it's alpha. Okay. Let's make this one positive pitching. So now for some reason alpha increased right here. Now CM is positive. Alpha will increase more. Alpha will increase more because it's always positive. But when the slope was negative, what happened? When alpha increased, you went below the what to say, CM is equal to 0 line. This is CM is equal to 0 line. You went below it when angle of attack increased. So what happened is CM became negative, and it became negative. So it has a tendency to decrease the angle of attack when CM is less than 0. But in this case, it continued increasing it. So this is unstable, and this is stable. This one is stable, and that is the reason why CM alpha is negative. And the reason for CM not to be positive is fairly simple, because you want to pitch the aircraft at a positive angle of attack. When the slope is like this, you are pitching it at 0 angle of attack, but you want to pitch it at some positive angle of attack, so you just shift this line upwards. So this is the point where you can pitch. You can't, you don't want to pitch here. So CM naught is not negative. CM naught is therefore positive, because you want to pitch the aircraft at a positive angle of attack. Okay, because you want to maximize L by D also while you're flying for range maximization, and that happens at some positive angle of attack. So for that reason, CM naught should be positive. I hope I'm clear now, right?
Yes, sir. Got it, sir.
Got it. All right. So if you guys want, you can leave I'll leave this meeting on for next 1 hour because I don't have much content. I just came from home. Like I had a 17-day vacation. Last 2 classes I took from home. I just came today, so I have this much only. I'll cover more things in the next week because I'm on the campus. I'll probably study and then teach you.
Okay, sir. Thank you.
Yeah, thank you. You guys also can be if you want.